This is the demonstration and protocol for Lab 21, Hormonal Control of Urine Production. In this recording, we're going to be going over the background of a little bit about how the kidneys work, which you'll mostly be getting in lecture, but this will cover some of it, with some emphasis on how urine is produced, the reabsorption secretion in particular of sodium, potassium, and water, and the influences of aldosterone and antidiuretic hormone, also known as vasopressin, on water retention and excretion. We'll go over the lab protocol for how we're going to investigate the hormonal control of urine, how to use dip strips, and just a little bit on how to do a microscopic examination of urine, and I'll show an example of the analysis of my own urine. So let's start our background here by talking about the anatomy of the nephron, the filtering unit of the kidney. Shown here is a sketch of a nephron. This is in its folded up orientation, which is more or less how they're found in the kidney. And you can tell that it's a little hard to figure out everything that's going on in here. I can point out the major parts. So, for example, in black here is the urinary tubule, starting with the Bowman's capsule, the proximal convoluted tubule, the loop of Henle, the descending and ascending limbs, and then the distal convoluted tubule, followed by joining onto the collecting duct here. And with the blood vessels in red, you can see the afferent arteriole bringing blood to the nephron, the glomerulus, where filtration is going to happen, the efferent arteriole taking blood out, and then that feeds into a set of peritubular capillaries around the loop of Henle and the proximal and distal convoluted tubule. Then this blood is heading back toward the renal vein. Of course, depending on whether this is a juxtamedullary or cortical nephron would depend on what kind of blood vessels you'd find here around the loop of Henle, but we're not going to get into that right now. Now, it's a little hard to see how this is all put together, so let's switch to a different, an unfolded diagram of the nephron that'll make it easier to talk about what's going on in this area. So here's an unfolded version of the nephron, which will be a little bit easier to talk about. And just to clarify everything, this was our Bowman's capsule with the glomerulus, the afferent and efferent arterioles. This first part of the urinary tubule, the proximal convoluted tubule, leads into the descending and then ascending limbs of the loop of Henle. Then we get to the distal convoluted tubule, and which joins onto this collecting duct. Now, let's talk a little bit about how this works in terms of urine production. Filtration, the first major step of this process, happens here at the glomerulus. Filtration is relatively non-selective. Basically, anything small enough to fit through the filtration slits and the fenestrations here at the glomerulus with its podocytes filters out into the Bowman's capsule. And roughly 20% of what's small enough to fit through. Most of it technically does stay in the blood, but about a fifth of it comes out here. And that total filtration amounts to a relatively large amount. We're talking about something in the scale of about 180 liters a day total filtrate in all the nephrons together. Now, as that filtrate passes through the proximal convoluted tubule here, most of it, roughly 2/3 of the water, is reabsorbed here. So most of what we filtered out gets taken back from the proximal tubule and into these peritubular capillaries, so it's returned to the blood. So here we are reabsorbing. Let's make a note of that in green. So we're reabsorbing. We reabsorb a lot of things, for example, glucose and amino acids, but we're reabsorbing, we're going to pay special attention here to sodium, water, and potassium here in the proximal tubule. And then here in the loop, in the nephron loop, or loop of Henle, we're going to reabsorb water from the descending side, and solutes, reabsorbing sodium and potassium, and chloride, but again, we're really only paying attention to sodium and potassium right now, from this side, from the ascending side of the loop of Henle. All of that reabsorption, what's going on here in the proximal tubule and the loop of Henle, accounts for more or less about 90% of what we filtered. We're still going to reabsorb a lot of what's left, but how much more we reabsorb is going to be variable. What gets reabsorbed here is what's known as obligatory reabsorption. That really doesn't change much. We always reabsorb that. But then how much we reabsorb here in the distal tubule and the collecting duct, that's going to be variable because our kidney needs the ability to adjust how much we reabsorb based on what we take in. So, for example, when you go to the movies and you get the small soda, which these days is something like a 64-ounce soda, you're taking in a lot of water if you drink that during the film. Now, that water is going to go to your blood, which is going to tend to raise your blood pressure. Our body needs a way to get rid of that extra water. And so, while we're still reabsorbing most of that water here in the proximal tubule and the loop of Henle, we want to get rid of more than we usually would so we don't keep all of that extra fluid, which means we need to turn up the amount of water we lose by reabsorbing less of it here. So we will reduce reabsorption of water in the distal tubule and the collecting duct. Likewise, if you are dehydrated, your body's going to want to lose as little water as possible, which means, again, you can't adjust the amount of water you reabsorb here most of the time, but you'll want to turn up the reabsorption of water in the distal tubule and the collecting duct so that you lose as little as possible in the urine. Similar principles apply to sodium and potassium balance. If you take in a bunch of sodium, you don't want to keep all of that. You want to regulate the amount of sodium in your body. So if you take in a lot, you're going to try to lose more, which means you will reduce the amount of sodium you reabsorb in this area specifically. And if you have too much potassium, you'll want to get rid of more potassium, so you'll reabsorb less or even secrete more potassium in this area. Since these areas are variable in terms of how much water and solutes they can reabsorb and secrete, we're going to look in this lab about what affects the reabsorption and secretion in those areas. That's largely going to be under the control of certain hormones. So the hormone aldosterone, I'll do this over here. Aldosterone, its major effect is to increase sodium reabsorption in the distal convoluted tubule. It also increases potassium secretion in the distal tubule. So under the influence of aldosterone, we will reabsorb more sodium here in the distal convoluted tubule. So we're going to reabsorb sodium, and aldosterone will add to that. We'll say aldosterone increases reabsorption of sodium. In this area, we also secrete potassium. And likewise, aldosterone increases how much of that we do. Now, in the distal tubule, because of the way in which we do this, where we use a 3-to-2 ion pump, the sodium-potassium ATPase, if I increase sodium reabsorption and increase potassium secretion, I will also increase reabsorption of water. So we're going to reabsorb water here as well. And aldosterone increases that as well. Now here in the collecting duct, we're mostly going to be looking at the variable reabsorption of water. So here we reabsorb water. And this is going to be controlled largely by the hormone, antidiuretic hormone, also known as ADH, or also known as vasopressin. Antidiuretic hormone increases the amount of water reabsorption in the collecting duct. So this increases water reabsorption in the collecting duct. So over here we'll say that ADH, or vasopressin, increases that function. Now, you can make some conclusions from that. For example, if I found that I was dehydrated, what do you think my body would do in terms of secretion of antidiuretic hormone? If I'm dehydrated, so my body does not have enough water, will I want to increase or decrease the amount of secretion of antidiuretic hormone? My guess would be that if I'm dehydrated, I'm low on water, so I want to lose as little water as possible, which means I'm going to secrete more antidiuretic hormone, which will cause me to reabsorb more water from the collecting duct so that I can keep it in my body. Here's another one. If I have hyperkalemia, which is the condition of having too much potassium in my body, what would it make sense for that to do to the amount of aldosterone I secrete from in my body? So if I've got too much potassium, aldosterone secretion is probably going to increase, and that will cause me to secrete more potassium here, which will cause me to lose that potassium so that I can remedy my condition of hyperkalemia. All right, so that's kind of the idea behind these hormones. Now we're actually going to look at how we're going to investigate this in this lab. So as we've just learned, water reabsorption in the distal tubule and the collecting duct is controlled by aldosterone and antidiuretic hormone, also known as vasopressin. So our theory in this lab is that if we can consume low sodium and also bring in extra water, the body responds to that by not needing to reabsorb the sodium and not needing to reabsorb the water. So it reduces aldosterone and ADH secretion. That means that the body will lose more of that water in the urine, and thus having more water in the urine will cause it to have a lower osmolarity, which will manifest in the kind of test we're doing as a lower specific gravity. This lab protocol actually starts the night before your lab. On the evening of the night before your lab, you, the subject, will need to track your sodium and fluid consumption after 5 p.m. For everything you eat or drink, you need to keep track of how many milligrams of sodium that contains and also how many milliliters of water you drink. To know the amount of sodium in your foods, you can look up foods in all sorts of online resources. There are even several apps for iPhone and Android phones that you can use for reference. But keep track of everything you eat between 5 p.m. and midnight. And after midnight, try not to eat anything else, and especially don't drink any water after midnight that night. The next morning, the first urine of the morning should be collected using the clean catch technique. You can find a summary of that at the link there, but the short version is use some sort of sterile wipe to clean either the head of the penis or the area between the labia, and then collect the urine. Go ahead and release urine into the toilet for a few seconds, then stop, then move the collection cup under the urine stream and put an ounce or two of urine into that. Then remove it, close up the sample. Then refrigerate that sample during the morning and then bring it to class. Your instructor should be able to refrigerate it at that point. During that day, you need to make sure that you consume a low sodium diet. The total amount of sodium you consume over the course of that day before your second urine sample should be less than 1,000 milligrams of sodium. You may need to plan that out using one of those trackers for knowing what's in your food. When you come to lecture, during the lecture, consume at least 500 milliliters of water. That's 16 ounces, but feel free to consume more. That should be purified or distilled water if possible. And then about an hour into the lab period, you're going to collect a second urine sample using the clean catch technique. And then you'll analyze both of those samples using a dip strip and probably also a urinometer. Here you'll see 2 urine samples. Sample A was taken on day 1, note the fluid and sodium consumption numbers. Sample 2 was taken after a low sodium morning and consumption of 500 milliliters of water. Note the distinct differences in color. We'll be using a hydrometer to measure specific gravity. That'll be indicated by the numbers that you see there on the stem. To demonstrate, let's try it out on some pure water. We float the hydrometer, and we read it where the meniscus hits the stem. Here you can see that the water has a specific gravity of exactly 1.000. Now, let's try it on the samples. First, we'll determine the specific gravity for sample A. Take a close-up here so you can read it. And now you can find the specific gravity for sample B. Turn it so you can get a better look. Go ahead and make a note of those two specific gravities.